So today we are going to tell what is the boundary condition of electric field. So boundary conditions means when the electric field transferred from one medium or passes from one medium to another medium which has different dielectric constant which is epsilon. Okay, so what will happen to the electric field, to its horizontal component, particular component? We will establish a relation between the horizontal component of the electric fields in two medium and perpendicular component of the electric field in two medium which has different electric permittivity. So before that, we always know that electric field is a conservative field. So closed integration of E dot dl along the work done by moving a unit positive charge in a closed path by an electric field is always equal to 0. And from Gauss's law we know closed integration D dot ds equal to q enclosed. D is nothing but electric flux density which is equal to epsilon naught times E. So electric field is a vector quantity. It can electric, so any vector quantity can be represented in the form of horizontal and vertical component. So that's why electric field can be represented as a horizontal component of the electric field and the vertical component of the electric field. So what is horizontal component? The horizontal component of the electric field, also you can say the tangential component, which is known as ET. Sorry, here we can give the vector sign ET, and En is the normal component. Okay, so horizontal component is a component of the electric field which is horizontal or the parallel to the boundary, and the normal component is the perpendicular of the boundary of two medium. So Et is known as tangential E, and En is the normal component of the E. So you can see there is a boundary which is between two materials. Epsilon 2 is the boundary, is the material with electric permittivity epsilon 2, and another medium 1, which has electric permittivity of epsilon 1. So when the electric field passes from one medium to another medium, when the electric field when the electric field E1 is the electric field in medium 1 and E2 is the electric field in medium 2. So E1 and E2 are the electric field in both the medium. So E1 is the electric field in medium 1 and E2 is the electric field in medium 2. So E1 has a normal component E1n and horizontal component or the tangential component E1t. Similarly, E2 has a normal component E2n and the horizontal component E2t. So we are going to establish the relation in the first case between the tangential component or the horizontal component of two electric field. So for that, what we have done, we have taken a closed path which is in the form of square around the boundary. So closed path has a height h and the width w. So we will calculate the work done by the electric field in each path and equate to 0, because the closed integration by the electric field by any path is equal to 0. So closed integration E dot dl equal to 0. So when we are moving, we are moving in path 1. Okay, so we know E1 T to W is the work done by the electric field in this path A. So E1n and dot H2 is the work done by the normal component of the electric field in this path B, and E2 and H by 2 is the normal component of the electric field in this path. Similarly, the direction of the E2t and this W, that path we are moving, is opposite or cos 180 degree. So work done will be negative along this path. So it will be E2t minus E2t W. Similarly, for this path, it will be minus E1n H by 2 minus E2n H by 2. So if you calculate it once, you can understand why it is coming minus, why it is coming plus. So you can say minus E2t E1n H by 2 and plus E1 H by 2 will cancel each other. Similarly, minus E2n h by 2 will cancel this. U1n h by 2 will cancel minus E1 h by 2, minus E2n h by 2 will cancel, plus E2n h by 2. So we are left with E1t dot w minus E2t dot w equal to 0. So taking this E2 minus E2t w in the right hand side, we will get plus E2t w, and w will cancel each other. So you can say E1t is equal to E2t. So you can say the horizontal component of the electric field will be same in both the medium which is defined dielectric. So the horizontal component of the electric field will not change. So now we want to establish a relation between the perpendicular component of the electric field. So let us take a boundary. So boundary we have taken. So we have taken a boundary which has surface charge density of sigma. So we assume that the boundary that is separating two medium has surface charge density sigma or rho. Rho is the surface charge density of the boundary. So we have taken the positive charges in the boundary. So now, according to Gauss law, we have taken a hypothetical surface, a mathematical Gaussian surface, which is cylindrical in the form. So we know close integration d dot ds equal to q enclosed. So d1n dot s. So the surfaces we have given name. S1 is the uppermost surface, S2 is the downmost surface, and S3 is the surface area of this side. So d close integration d dot ds equal to q enclosed. So d1n dot, so perpendicular component of the electric flux density is d1n, which is present in the surface S2. Sorry, it will be S2, and this will be S1. So d1n dot S2 and minus d2n dot S1. Why minus? The surface S2 and S1 are in opposite direction. So d1n dot S1 minus d2n dot d1 dot d1n dot S2 minus d2n dot S1 plus 0. Why it is 0? The flux that is coming from the lateral surfaces of the cylinder will be equal to 0, because the surface vector are opposite to each other. So we can, when we do the overall integration, it will become 0 equal to q. So we know it's a cylinder, so upper surface and lower surface have same surface area. So thus S1 will be equal to S2. So you can, from here we can say d1n dot and S1 equal to S2, which is equal to, we can assume S. So d1n dot S minus d2n dot S equal to rho S. Rho is the surface charge density at the boundary. So rho dot S is the surface of the cross section area of the cylinder, which is equal to again S. So rho S dot S. So d1n minus d2n equal to rho S. So we can say the difference between the electric flux density of both medium is equal to rho S. Rho S is nothing but the surface charge density of the two medium at the boundary. So in some cases, in maximum cases, the rho S is equal to 0. So for that we can say d1n minus d2n is equal to 0. So you can say d1n equal to d2n. So d1n is the normal component of the electric flux density of medium 1, and d2n is the normal component of the electric flux density in medium 2. So the component of the electric flux density in medium 1 is equal to medium 2, and again d can be represented as epsilon times E. So we can substitute the value of d in the equation. So you can say epsilon 1 E1n epsilon 2 E2n is equal to epsilon naught E2n. So you can say the ratio of E1n and E2n is equal to epsilon 2 by epsilon 1. We can say the normal component of the electric field, the ratio of the normal component of the electric field is inversely is equal to the inverse ratio of the electric permittivity of the medium. So from this we can say that. So thank you for today's lecture. Hope we will see in the next lecture.